So, good morning, everyone. My name is Felipe Andrade. I'm an employee here at DYNAmore, and welcome today to this DYNAmore Express session. Today, we're going to have a talk from my colleague, Dr. Steffen Mattern. He will give us an overview about the possibilities, how you can simulate airbags in LS-DYNA, what are the different types and possibilities that you have in that regard. We will start quite soon. I would really please ask you to mute all your microphones. Today here we have a small technical difficulty. Me as a host, I'm not being able to mute you. Normally we can do this, but today I don't know why it's not really working. So I please ask you to mute your microphones. Thank you. It's a button on the down part here on the bottom part of your app. So please mute your microphones. And well, if you have questions, I kindly ask you to write them into the chat. You can do it during the talk. I believe we are going to do the questions at the end of the presentation, but in the meantime, you can write all your questions if you want into the chat. We will have some time at the end for a few questions. And also at the end of the presentation today, I will kindly ask you to evaluate or give us a feedback about this talk. I will also write into the chat a link where you can evaluate the talk today. And well, I guess that's it. Steffen, if you are ready, I believe you can start with your presentation. And okay, so let's start.
I'm ready. Thanks, Felipe, for the introduction. And welcome everybody to this week's DYNAmore Express webinar about the different possibilities for modeling airbags in LS-DYNA. My name is Steffen Mattern, as Felipe already introduced me. I'm working for DYNAmore since 2012, mostly giving customer support for automotive occupant safety and crash simulation. Besides that, I'm giving seminars, for example, the introduction seminar, the so-called beginner's course, and also the airbag seminar, the regular airbag seminar is what I'm doing. Today, we will start with a short introduction, followed by a comprehensive presentation of the 3 airbag modeling techniques available in LS-DYNA. These are the uniform pressure approach, sometimes also referred to as the control volume method. Second, the arbitrary Lagrangian Eulerian method, and finally, the corpuscular particle method. It has been a standard application to model airbags in modern CAE models for occupant safety simulation for many years now. At first, the focus was on capturing the impact of the dummy to the fully inflated airbag. With today's sophisticated and detailed CAE models, we also want to capture more details with our airbag models, such as the influence of different folding schemes, the influence of vent holes or sizes of vent holes, positions of vent holes, the airbag's interaction with the surrounding in the early deployment phase, for example, to discuss the opening of an airbag's cover, and also out of position load cases where the occupant is close to the airbag at the time the airbag is fired. This increasing demands lead to the 3 different modeling methods available in LS-DYNA. Due to LS-DYNA's philosophy of backwards compatibility, all the 3 methods are still available and can be used in current versions. However, regarding the implementation of new features and improvements of the methods, the focus clearly lays on the CPM method today, which is today's state-of-the-art airbag modeling technique in LS-DYNA. Besides the method for the simulation of the inflation, of course, there is more one has to know in order to build a CAE model for an airbag, such as material modeling, contact formulations, and so on. In the following, let's say 45 minutes, probably 1 hour, we will briefly discuss the 3 different approaches. We will have a look at some theory and very briefly at the most important keywords. Here, I will focus on some of the important parameters, while I will skip some of the others. You will find more details in the keyword manual if you are interested. And if you want to know more about airbag modeling, about the state of the art of airbag modeling in general, including all the other topics already mentioned, please visit our advanced course. The next possibility would probably be the LS-DYNA compact seminar, which is also available via WebEx. I guess it's scheduled for early November next time. Please visit our website here for more details. Okay, let's start. As already mentioned, there are 3 different methods available in LS-DYNA. The oldest is the uniform pressure approach or control volume method, where the gas is represented by a pressure boundary condition which is assumed to be uniformly distributed inside the airbag's volume. The second approach, the Arbitrary Lagrangian Eulerian Method, or ALE, had already been available in LS-DYNA before it was used for airbags, for modeling fluid structure interaction, for example. It could successfully be applied to airbags first, and special dedicated keywords such as airbag ALE have been implemented later. The newest method, most recently implemented method, available in LS-DYNA is the Corpuscular Particle Method, short CPM, which is based on the kinetic molecular theory well known from thermodynamic physics. Okay, let's start with the uniform pressure approach. The uniform pressure approach is based on the assumption of a uniform pressure distribution, of course, as the name says, inside the control volume. The fluid, which in our case is the gas domain, is here represented by a pressure boundary condition, which applies forces perpendicular to the defined surfaces. Hence, there is no discretization of the fluid. The formulation is based on a balance of energy into and out of the airbag, and the work done by the pressure for the change of the volume. There are different uniform pressure models available in LS-DYNA. If you take a look at the manual, rather simple models are still used nowadays, for example, for modeling vehicle tires. The most common model for occupant safety airbags is the so-called hybrid model, where the gas mixture used for the inflation can be specified by defining the properties and fractions of the different gas components. I will come to the keywords later on. Here we see the energy balance equation again in a different form. I don't want to discuss this in every detail. On the right side, you see the parameters specifying the properties of the gas, which are the temperature-dependent heat capacities, the molecular weight, and the fraction of the gas component. And finally, the molecular weight of the mixture is then computed internally, as well as the resultant heat capacities. Well, as I said, I don't want to discuss these formulas in detail. I just like to focus on the fact that the energy balance, the overall energy balance, is evaluated using the gas mixture, while the user has to input the properties of the different fractions, which makes the model very convenient to use. You will find further details also in the theory manual if you are interested. All the uniform pressure models start with the keyword airbag, followed by the same first cards. So first it is necessary to specify the closed volume forming the airbag by shells or segments. The normal vectors of the shells, or the segments in this case, shall point outwards of the airbag volume. This is something I always mention at this time in the airbag course, because for the recently used CPM method, it's the other way around. There, the normal vectors are supposed to face inside the airbag volume. Via SID and SID type, we define the ID of the set defining the airbag and what kind of set we want to use. So either it's a segment set or it's a part set. The next cards, there are more. You see, this is card 1A, and there are more optional cards available from B to F and 2A to B and so on. You can see the details in the manual. Here you can define all kinds of settings which are used by all the different uniform pressure models. For example, just to make one example, a mass-weighted damping factor here. Then followed by the specific cards for the different uniform pressure models. So this card is specific for the model simple pressure volume, which I choose here as an example because it's mostly used for the modeling of air-filled tires, still up to date in the current crash models. Here we simply specify the relation between the change of volume and the change of pressure, which can be either constant or described via a curve. The second model I chose, as already mentioned, it's the most sophisticated uniform pressure model, is the airbag hybrid. For example, here you can define the variables indexed with 2, 3. You see here C23, LC, C23, and so on. The variables indexed with 2, 3, they specify the behavior regarding the outflow. Everything which is which defines variables regarding the outflow from the airbag volume are defined here. So, for example, fabric leakage or vent leakage. N-gas here defines the number of gas components for the mixture, and in the following, the describing parameters as well as the mass flow rate, temperature, the mass fraction for each of the gas components are expected. These two cards 4 and 5, they are repeated for the number of gas fractions we have in our airbag. Besides the mentioned two, there are further uniform pressure models available via the keywords given here. You can take a look at the manual if you are interested. And an important option I also like to mention is for the hybrid model is the jetting option. This is an enhancement of the hybrid model, which allows a local scaling of the pressure forces. This somehow tries to take into account local gas flow effects. I will show this effect in a simple example on the next slide, and I will also discuss its limitations later on when we come to the more sophisticated methods. One last comment on the keywords. In order to model chambered airbags, one has to define one airbag for each chamber, and the connection or the interaction of these chambers is then defined via this keyword airbag interaction. So let's summarize the uniform pressure approach already. On the pro side, it's numerically very efficient and robust since it deals with pressure boundary conditions only. So the model setup is rather simple, as the gas is not actually represented in the model. It's not really discretized, but it's only described by its properties. On the other side, due to its simplicity, local effects from the gas flow cannot be captured precisely. This is especially important in the first few milliseconds, the deployment phase of the airbag. And since there are a lot of non-physical tuning parameters, it requires some experience to work with this method to work with validated or to validate airbag models or to apply changes to validated airbag models. So the first example I like to show is a simple inflation test of a very simple airbag, of a cushion, using airbag hybrid. And as you see, take a look at the video. It looks rather static since the pressure distribution is uniform in the entire airbag volume. So assuming the gas generator to be somewhere in the middle of the airbag's volume, the inflation looks much more physical when you add the jetting option, the airbag hybrid jetting. So you can define directions or vectors of the gas flow. But I will show you the video again. You will see that it's some more aggressive. The gas seems to be directed in some way, but you have to keep in mind that this is just the result of a scaling of the pressure boundary condition. So the model will, for example, not be able to take into account for changes of the jetting's direction due to interaction of the airbag with its structure. I will discuss this on the next slides, and you will understand why this is a limitation. We will go on and come to the second approach, the so-called Arbitrary Lagrangian Eulerian Method, or ALE. First, let's summarize our limitations again. We already discussed the limitations of the uniform pressure method before. So now, with an increasing complexity of the overall CAE models used for the crash simulations, the airbag's deployment phase is now expected to be represented as well. So we want to extend our fields of simulation to, for example, the opening of the airbag cover, the interaction of the airbag with its surrounding during the deployment phase, and in the consequence, the so-called out-of-position load cases where the occupant is not in the expected position while the restraint system is triggered. This was actually the first motivation for looking beyond the uniform pressure approach. And you can see a typical example here on the right side, a child dummy. This is only a model, but imagine a child is sitting on the lap of an adult, which you shouldn't try at home. And it is impacted by the deploying passenger airbag. So let's take a look at the animations. This is an animation using the regular hybrid airbag, and on the lower side we have the jetting option activated as well. But as you see here, the acceleration signals of the head and the thorax, they look pretty similar. So even activating the jetting option did not change anything. What did we want to change? We saw from the experiments that we expected higher peaks, higher acceleration peaks in the beginning of the deployment. This is where the dummy's head is trying to, or is starting to move away from the airbag. And this is the point where also the jetting won't help, because the jetting's direction won't change. The dummy's head will be will turn backwards, and the jetting's direction will stay the same, and it will miss the dummy's head. So we expected higher accelerations in the first few milliseconds. So what to do? Now let's go 2 steps back. The idea came up to use a method for the simulation of fluid structure interaction, which has already been available in LS-DYNA, the Arbitrary Lagrangian Eulerian Method. Here, the structure and the fluid domain is discretized using finite elements, which would lead to large deformations in very bad element shapes when using standard finite elements for the gas, as we have pretty large deformations compared to structural materials. So there are different solutions to overcome this. This is what I want to show you. This is what you see here. If you have a very soft material, you see very large deformations here, which is not so good for standard finite elements. So there are different approaches to face this. For example, mesh adaptivity, which is quite difficult and numerically expensive, especially for volumetric elements. Strategies to prevent elements from being heavily distorted, so-called smoothing algorithms, they are applied within the ALE approach, which I will discuss briefly in the following. So you see, due to the smoothing algorithms, the mesh looks rather nicely here, still after deformation. So in the very first pages of every continuum mechanic textbooks, you find these kind of pictures, the so-called continuum potatoes. And you also find the description of two ways of looking at things, the so-called Lagrangian way on the left side, where the observer is sitting on the material point, and the so-called Eulerian way on the other side, where the observer is sitting at a fixed point in space. And an interesting fact, which I like to mention here, is that the Lagrangian way has actually been introduced by Leonhard Euler, and the Eulerian way has been introduced by Bernoulli and d'Alembert. So these people were modest enough not to use their own names for their own methods. So the ALE approach now somehow combines these two ways to complete a time increment. So in order to simulate this motion, two steps are performed. In the first step, the Lagrangian step, the mesh is actually deformed as we know it from standard finite elements. And this is then followed by mesh smoothing and the so-called advection, where the element variables and momentum are transported in order to receive the deformed geometry in a smooth or even completely restored mesh, as we see it here. So here, this is the deformed mesh, and then we perform the smoothing in order to reduce or even to eliminate the mesh deformations. We will not go deeper into detail, but as you can imagine, this increases the complexity and hence the numerical effort of a single time step, of course, because additional equations have to be solved. Compared to our standard finite elements, we can now have different materials sharing the same element. In other words, any material can flow through a defined Euler domain, fixed in space, or an ALE domain, which would be a moving domain. And interfaces between these materials have to be traced and reconstructed, and stresses have to be iterated on element level. So for a fixed Eulerian domain, this would probably look like this. And also a moving ALE domain is possible. So obviously ALE can be used for all kinds of materials undergoing large deformations, such as fluids and gases, but also solid materials, for example, foams. These materials often are contained by structures, and these structures would be modeled using standard finite elements. So this requires also the possibility of interaction between Eulerian or ALE and Lagrangian parts, which is also available in LS-DYNA. These features can be applied to model airbags by using standard finite elements for the fabric and the structure, and ALE for the gas inside and outside the airbag. So as I already said, ALE had been available before it was applied to airbags. In order to improve the usability, a dedicated keyword, Airbag ALE, is available today, where some features of other ALE-related keywords are combined. In other words, you can probably set up an ALE airbag without even using this keyword, this Airbag ALE keyword, but in this seminar today, I will focus on the Airbag ALE. So the first cards, because it's a dedicated airbag keyword, the first cards look pretty similar to the airbag hybrid. So you recognize these things where you define the closed volume, and pressure and temperatures and things can be defined. And also there is even a possibility to switch back to the uniform pressure method at some point in time. Will come later in the keyword. Card 3 contains some specific settings for the coupling of ALE with Lagrangian parts. If you are used to ALE in LS-DYNA, these similar options are also available in the keyword constrained Lagrangian solid. So this would be the connected keyword to this card here. Card 4 allows the definition and the characterization of vent holes. So you can define dedicated parts or part sets to be considered as vent holes where leakage is allowed. Then card 5, this is a special card because here the fluid domain is, let's say, discretized. So you can specify the ALE domain by parts meshed in advance in pre-processing. So you can mesh them by yourself, or you can define a box-shaped geometry that is meshed by LS-DYNA during the initialization. And then additionally, you have parameters for automatic motion and size adaptation of this domain. The following cards allow the specification of the gas and the surrounding air properties. Compared to uniform pressure, the position of the gas generator as well as the direction of the flow now, actually matters. It actually makes a difference where the gas is flowing inside the airbag's volume. And this can be specified in card number 9. So here you can specify orifices and their directions. The orifices are represented by nodes, and the directions are represented by vectors defined here. And of course, the gas cards are repeated for each gas component, and the orifice cards are repeated for each point source in the model. So much for the keyword. Now let's take a look at the results for our out of position example from before. Let's take a look at the animation. You can now see, I will stop the animation here. You can now see that you can see a fringe plot here shows the pressure distribution, and you can clearly see that the pressure is not uniformly distributed in the airbag's volume, especially in the beginning of the deployment. Yeah, so this is exactly our critical point. So let's watch the movie to the end. It's nice and colorful. And on the right side, you can now see the results, and these are the peaks I was talking about. So now, due to the simulation of the local gas flow effects, we have a more realistic behavior during unfolding, and hence the expected higher accelerations at the dummy's head and at the dummy's thorax. Okay, let's already conclude ALE. I like to start with the pros again. It's beneficial to discretize the fluid domain and to compute real fluid structure interaction here. Since the uniform pressure approach is clearly wrong, in the early phase of the deployment. This assumption of uniform distributed pressure is just not right in the beginning. Okay, so Also regarding post-processing, the discretization of the gas creates some more opportunities. You can really take a look at the flow, at the directions of the flow, and so on. On the other hand, the method is, as you can imagine, considerably more expensive regarding computational time. Also, pre-processing turns out to be rather complex compared with just having to define the control volume. Yeah, you have to take care about the gas. You have to model, discretize or something the gas domain, which was not necessary before. Another drawback is in the multi-material approach. Since the airbag's fabric cuts the ALE domain, elements on this intersection, you can imagine they may be partially inside and outside of the airbag. Part of the element is inside, a part of the element is outside. Due to numerical accuracy issues regarding these advection algorithms I was talking about, this sometimes leads to unwanted leakage. This was some kind of problem in this method. So today, even if it's rarely used for occupant safety airbag, ALE is applied to fluid structure interaction problems still. So I have two examples two current examples. First, you see a partially filled bag partially filled with fluid, where this is very similar to an airbag. The fluid is modeled using ALE and the structure is modeled using Lagrangian element, but it's also possible the other way around. You see a foam block impacted by a ball where the ball is rather stiff and modeled with Lagrangian finite elements, and the foam block is here modeled with ALE. Okay, so far for ALE. Now we come to the third and, as I already said, most recently implemented method, the so-called Corpuscular Particle Method, or short CPM. The user's wish, I want to start what the user was expecting for the new method to be able to do. So the user's wish was for a method providing accuracy comparable with ALE, especially regarding the early deployment phase, but requiring less computational effort. So let's wish something. So the developer's idea was to go for a particle approach based on the kinetic molecular theory, which is already known, which is well known from thermodynamics, and so to discretize the gas with a finite number of particles. The application of individual particles seemed promising here regarding the parallelization in the context of MPP, but there was a problem, and the problem is the number of particles. Since for a typical gas mixture, the number of molecules inside an airbag would be in the order of 10 to the power 23 to 10 to the power 24. So this clearly might be a problem. So there have been some things to think about for the developer, how to make the general concept of the kinetic molecular theory fit into a numerical code like LS-DYNA. So I will try to summarize this very briefly in the next slides. The kinetic molecular theory is based on different assumptions regarding the size, the motion, the interaction of molecules making up a gas. These assumptions are the distance between the molecules is assumed to be large compared to their size. In other words, there are only a few molecules in a control volume surrounded by a lot of nothing. Collisions are assumed to be perfectly elastic. Molecules obey Newton's laws of motion, and molecules are in random motion. Once again, these are the assumptions of the kinetic molecular theory. This has nothing to do with LS-DYNA. This was already theoretically available way before LS-DYNA. So after some theory that I want to skip for now, one conclusion is that under specific conditions, it is allowed to represent the gas with a smaller number of larger particles and still obtaining the same pressure in the control volume. This is, so to say, the most important step leading to the corpuscular particle method. Because, yeah, to summarize this, because it's not possible to individually represent each single molecule by one particle, the system is reduced from many molecules to a few particles by making sure the translational kinetic energy, this is the important step, by making sure the translational kinetic energy remains constant, the predicted pressure will also stay the same. So since the particles can move independently and only interact via contact with each other and with the airbag's fabric, the pressure will be automatically high where the particle density is high and low where there are only a few particles. So we will have high pressure where we have a lot of particles automatically. So finally, the corpuscular particle method is fully based on the kinetic molecular theory with a system reduced from many molecules to a few particles. The particles are spherical in shape for efficient contact treatment. A balance between translational and kinetic energy and vibration and spin is internally enforced. This is the part of the theory we skipped today. But this allows for the reduction of the system in the first place. Due to the reduced number of particles, the pressure signal contains a considerable amount of noise, which is partially removed by an internal smoothing algorithm, but still, especially when the pressure is evaluated using a rather small patch of elements, or if the number of particles is low, so for example, at low pressure events, the result can still be quite noisy. So let's go for the keywords. The central keyword for the CPM method is called airbag particle. Since the method has been constantly developed over the last years and still is, to be honest, the keyword became rather complex, and recently some new keywords around airbag particle have been introduced in order to further enhance the method. So the first strategy was to enhance more and more and add more and more lines and parameters to the airbag particle keyword, but nowadays it seems that we transport information to other keywords. So we will now, as before, we will take a short look only on the most important parameters. So on the next slides, I will pick some of the parameters and skip some parts just to focus only on the basic settings. The first card starts similar to the other airbag models with a definition of the control volume. But here you see there is a second set. This is the first set, which can be defined via a part set or a segment set or something else. And we have a second set here because now we have to separate the internal parts from the external parts in order to tell the algorithm which is the surrounding of the airbag and which is inside the airbag, but also in the interaction with the particles. The block parameter here controls whether or not particles are allowed to leak through the vents or through the fabric if they are blocked by a contact situation. So, for example, if you during unfolding, the vent holes are blocked via due to contact, leakage through these vents will be prevented or not with a you set block to 0 or 1. The second card starts with NP. This is actually the discretization of the gas. This is the total number of particles. And as it is with other discretizations, it's more or less to say the more particles you use, the better the approximation is. So this is the discretization parameter. The second parameter, unit, I like to mention this because it's very unusual to LS-DYNA. Since normally everything is expected to be in consistent units, but CPM internally uses, for example, the universal gas constant, and hence it requires knowledge of the unit system in which the model is set up. So here you have to specify in which unit system your entire airbag, or so to say, the entire CAE model you're working with is set up. Atmospheric temperature and pressure are defined here as well as the number of vent holes. And finally, we also have the opportunity to switch to uniform pressure at a certain point in time, as before with the ALE method. And this, I like to give a recommendation. This especially allows to use uniform pressure at a very early development of an airbag model to save computational effort by switching to uniform pressure right after firing. So this is what we recommended to use. If you set up a new model and you like to run computations quickly, then you can use this switch to switch right in the beginning. So you enter your parameters for the particle airbag, but you run your first computations actually with a uniform pressure model. We usually do not recommend to switch to uniform pressure in a production airbag model somewhere during the simulation. In card number 4, as you realize, I skipped card number 3. It will be on the next slide. In card number 4, we specify how initial air is modeled. That is air that is initially inside the airbag. Further, we specify the number of gas components and the number of orifice nodes, similar to the ALE parts before. With CHM, this is here, we can reference another keyword. It's called define CPM chambers. And this is used here to model airbags with multiple chambers. So in contrary to the uniform pressure, we now, if we have a multi-chambered airbag, we only define one airbag particle keyword, but defining the multiple chambers by referencing define CPM chambers model here. So let's go to card number 3. If you may not use standard unit systems, then you may also introduce your own scaling factors here. To be honest, I have never seen something like this in production airbags, but it's possible. And here we make a short skip to card number 8 because we already mentioned in the initial air flag, and this initial air flag set activates card number 8. Here the properties of the gas located in the airbag before deployment are defined. It's usually air, but it can be anything. Initial air can be represented using the uniform pressure approach, but it can also be represented using particles. In the latter case, the number of particles used for initial air must be specified. And it should be computed using this equation here, but I have a hint. If you don't want to manually compute it, you can use LS-DYNA to compute it, because LS-DYNA will print a warning message if the input value is too far off. So what I usually recommend is you can enter a wrong value first, like 1 particle or something like this. And then you can run one initialization and you take a look at the message file and you look for this specific message here. And then LS-DYNA will tell you the number of particles suggested. But you have to make sure if you change the number of particles, NP, the number of overall particles, this number will also change. So from time to time, we should look into this warning message. Depending on NP data was a parameter from card number 1. An additional number of cards are expected here, defining parts or part sets with so-called heat convection properties. This feature is used to take into account energy dissipation, energy from the gas dissipated over the fabric. Card number 7 is repeated for each vent. The number of vents were specified in card number 2, n vent. A vent is represented by a part or a set of parts included in the airbag definition. So the vent holes are usually not actually holes in the volume, but they are represented by finite elements as well. The algorithm works by particles actually impacting these parts are then removed from the control volume. This means that gas is leaking through the vents. Different options are available to control the effectivity of the vent as a function of time or pressure. So you can have vents, for example, which open only after a specific time. Card number 10 is repeated as from the models before. It's repeated for every gas component. So it's repeated n gas times. N gas is the parameter specified in card number 4. Here the properties and the mass flow rates and the temperature profiles are specified for each gas component. And finally, in card number 11, as many orifices are specified as requested via this NORIF parameter already from card number 4. The orifices are either represented by nodes or by shell elements, while both of them should not be part of the airbag's structure. So we usually use massless nodes, independent nodes, and tie them to the structure, for example, to the gas generator via constrained extra nodes, something like this. Here you can also make different settings. For example, to adjust the vector of the particle's velocity generated at these nozzles. So for nodes, you have to specify a vector. For when you use shell elements, you automatically have a vector, the normal vector of the shell element. You can make settings here. So these were a lot of keywords and a very quick overview. And this is how finally a typical airbag particle keyword looks like in the input file. Here you see the number of particles is parameterized. You can do this. You can set up a parameter in the top of your keyword to quickly change the number of particles. The airbag has 4 vents and 2 orifice nodes, and vent equals 4. Number of orifice nodes equals 2. And the 4 vents make 4 lines here. So these are the part IDs of the 4 vents, and these are the effectivities, and so on and so on. And the number of orifice nodes lead to 2 lines here, node number 1, node number 2, and here the vector ID is referenced. The model contains 1 gas component. This is here, n gas is equal 1, leading to this line here, where the mass flow rate and the temperature profile of the inflating gas is defined. And it also takes into account initial air. With this 1 here, the initial air is represented by a uniform pressure approach, and the properties of the initial air, the pressure and the temperature and so on, defined here. As I already mentioned, there are different keywords available connected to the airbag particle, which provide some more flexibility and additional options and so on for the definition of the gas properties, for example. Also for the vents, there is a keyword, and for the chambers, as I already mentioned. The content of these keywords and how they are integrated into the airbag particle will be discussed in the advanced seminar. So, compared to the ALE method, CPM proves to be rather simple to use and numerically robust. It's setting up an airbag model is quite comparable to airbag hybrid, which also makes it relatively easy to convert existing models from uniform pressure airbag hybrid to CPM. The accuracy, especially in the deployment phase or in out of position situations, is quite good, which makes the CPM method today's state of the art for modeling airbags for occupant safety simulations. We are actually running full car crash simulations with 4 or more particle airbags today, which scales pretty well using MPP versions on many processors. As a drawback, yeah, we have to mention the noise in the pressure signal. I already mentioned this, especially at lower pressure values where less particles are present. This, yeah, can be a problem. It also has to be clarified that CPM is not able to describe the actual flow field accurately. So, yeah, it's somehow limited to the macroscopic view on the airbag. So you somehow use this method to simulate the deployment of your airbag, but you cannot use it to deeply look into the flow of your gas, into the local flow effects. So I will close today's seminar with 2 examples. First, a simple inflation test of a flat airbag. So it's a very simple model. It can clearly be seen how the deployment kinematics of CPM automatically match with the airbag hybrid jetting. But I use this comparison here because here the jetting is realized by non-physical parameters. I have to define vectors and directions and scaling factors in order to achieve this kind of localization of the inflation, and this is automatically, let's say, automatically integrated in CPM. As I define the location of the orifice nodes, I automatically have this local effects here. In the second example, I show this is an impactor test with a folded airbag. It's kind of a typical validation scenario of an airbag model. So again, we compare the hybrid model with and without jetting with the CPM model. This is, by the way, this is what you see if you. This is actually the LS pre-post doing this video, but you can also visualize the particle using other post processors. So these brown dots inside the airbag's volume, these are actually the particles. Comparing the results, we see some positive influence of the jetting option in this example on the acceleration, while the pressure signal is mostly unaffected. Here the particle approach shows a significantly higher pressure peak in the beginning of the deployment compared to uniform pressure. In this example, the impactor can only move upwards. So yeah, it will not affect the gas flow direction as it was the case in the example with the child dummy before. So if this would be the case, the limitation of the airbag hybrid jetting regarding the adjustment of the jetting directions would also be a problem here. Okay, so with this summed up conclusions, I will just leave this slide here for the discussions. I want to close the talk for today, and I want to thank you for your attention. And if there are questions in the chat or questions probably live, you can ask. Yeah, thank you very much.
Okay, Steffen, thank you very much for this interesting presentation. I'm not an an airbag expert, so I learned a few things today. Okay, great. So I would like to thank you very much, Steffen, again for your presentation. Thank the participants for being here today. I'm just putting here into the chat a link to an evaluation. So please, if you have some time, just kindly answer that. It will help us. And this presentation will be available also on the internet later on in a few days. The PDF of this and also the talk that we had today here, it's going to be available on YouTube, on our YouTube channel, I believe in a few days also. So if you want to see it again, you can do it using our YouTube channel. So thank you very much, everyone. And I wish you a nice day and also a nice weekend.